Thank you so much for coming. Today we will be talking about very interesting and very important topics about privacy, confidentiality, and post-quantum cryptography. And with me on the stage to make it much more interesting, by the way, let me introduce myself as those gentlemen will join me. I'm Nelly Porter. I'm Director of Product Management in Google, owning encryption products, confidential computing, and definitely post-quantum. And again, with me, Amit Patil. He's, again, engineering director owning exactly the same area, my partner in crime. And Anand Pashupathy, who is VP and GM in Intel, and we'll be talking about what Intel is doing in these areas as well. And we also will have discussion group an hour later. If you will have any questions, anything you would like to discuss with me, more than welcome to join. So let us start. This topic is more about confidential AI. And it's again why confidential AI is becoming very critical, because protection of data is going in training, fine-tuning, or inference is becoming completely paramount. And when our customers that creating their own models, bringing those models to GCP, they want to protect IP. So confidential AI is ability for us to protect the data and model, and with agentic AI, even agents, end-to-end. What we talking about? So if you will leave this session today and will remember only this slide, I would highly appreciate it. So confidential AI consists of, no surprise, confidentiality. And it means we encrypt data and model across end-to-end to ensure that when this model or data processed in memory is continued to be encrypted. When data is traveling over the wire, it also needs to be protected, encrypted. And when anything stored at rest, it also needs to be protected. It's all what confidentiality is all about. The second thing that very important is integrity. When we're talking about integrity, it means guarantee that nothing is changed, nothing is tempered. And it's critically important because if you have no trusting relationship with what is happening with your workload, and somebody modified your data or model, that you know that your situation is not very good. And the third point, I think is unique to confidential compute. It's cryptographic verifiability. A lot of technology, maybe you're familiar with, is again trying to provide cryptography or encryption or integrity authentication. But ability for you to verify it and present this evidence to your auditors exists only and only with confidential compute. So ability to provide cryptographic proof that confidentiality and integrity exist is what confidential AI is all about. Why it's important? My customers coming to us and saying, okay, when we bring in our data in and our models in, huge IP, we want to ensure that you, Google, or your Google high privileged admins would not be able to see it, to access it, have nothing to do with that. And how we will remove our admins from the trust circle? It's all about confidentiality, integrity, and cryptographic proof. We have solution also on the market called confidential space when we capable of doing even more. Some customers coming and saying, okay, we not only want to remove your highly privileged admins, but also ours. Because we want to demonstrate to our end customers and end users that we don't do anything fishy. And it's exactly what confidential compute can do to provide integrity and confidentiality, not only systems that we build, but also workloads that are running in this system. We sometimes refer to that, to confuse all of you, as trusted execution environments, or TE. When you hear the TE sense, know that it's related to confidential environment. And all confidential environments, why it's so interesting, is built on hardware root of trust. It means that all of this encryption of memory and integrity is done by the keys that embedded in the hardware. So we, Google, have no way to, or you, to extract it, export it, update it, lifecycle it, nothing. It's actually absolutely hardware-based security that can be validated and should be trusted. And to show you what it means in practice, let me invite Anand on the stage, because one of hardware-rooted environments that we use is Intel-based, and it's Intel-based TDX. Explain to us, Anand, what TDX is all about.
Yes, thank you. Thank you, Nelly. Thank you, Amit. Thank you, the team Google, for having me. As Nelly said, my name is Anand Pashupathy. I run a product security and assurance organization at Intel, and confidential computing is something that Nelly and I have been partnering on for at least 5 years now. I'm going to take you back a little bit, and I'm sorry, I have a little bit of cold, so if my words are a little unclear, my apologies right now. I want to take you back to, we truly as an industry are at a tipping point. I have been saying, and I've heard Nelly say this before as well, that AI is going to be the fuel that's going to push confidential computing forward. And it comes with its own challenges as well. I feel there is a friction between pushing that forward, because while AI has all this hype associated with it, the actual technology that is foundational on trust is slowly catching up. There is regulatory compliance, there is sovereignty concerns, there is user and trust issues, and we have to collectively overcome that. And hopefully I will be able to share with you today the technologies that is going to enable that moving forward for you, for your business. I'm going to start with Intel Trust Domain Extension technology, with Nelly fondly called Intel TDX. It's what we call very fondly within Intel a trusted execution environment. You hear that in the industry as well. It's really when data is being acted upon that is opaque to anybody else outside of that. So you give it that hardware-enforced isolation of your code and of your data, right? So nobody has access to it, nobody can manipulate it, and it's secure from that point of view. So isolation is necessary but not sufficient. As Nelly said before, attestation is a key element of confidential computing, because you want to give that confidence to your customers who are running the workload inside a GCP environment, that workload has, and the confidential VM has the highest level of integrity and nothing has been tampered with. So that level of attestation proof, cryptographic proof, is what TDX supports. And at the end of the day, you have access to your data. You control it. You do not, you will have to give access to that data to somebody else. Otherwise, you continue to maintain that opacity of your data. Okay, now let me tie this value chain and tell you how things like TDX helps you in this journey. There's a lot of hype, as I said, about AI. Everybody wants to maximize their AI value in whatever they are implementing, even in the confidential computing environment, right? Or with a confidential computing environment. But then, in order to get to value, which is about cost savings, revenue generation, making agents talk to other agents, chaining them together, getting value out of all of that infrastructure, you have to go through a utility layer, right? You need to make sure that you have the agents that are accessing your data in the appropriate fashion. You have to make sure that people are trained to do all of that. But before you get to value, you have to get to utility. And before you can get to utility, it's built on this foundation of trust. Can you answer the questions, hey, am I giving access to data that is confidential of my enterprise out to the public? Am I making sure that there is no unauthorized access of my data happening, right? So my conjecture, or I shouldn't say a conjecture, my assertion is that we have to make sure that the AI trust and safety layer has to be secure in order for people to deliver that value, which is what Intel TDX allows you to do, right? It will allow you to enable trust in the system in order for you to deliver that value at the end, okay? So with that assertion that Intel TDX is foundational, now let me tell you what the range of options that are available today on Google Cloud and the options that are coming up. So on the left extreme is Intel TDX with AMX, which is Advanced Matrix Extension Technology. I talked about this last time I was at Google Next, where we said for small language models, if you need acceleration, you can achieve up to 6x performance boost on a Xeon CPU with AMX. It's available today on GCP. The next one over is Intel TDX with AMX, and this is where you get your confidentiality. You get, the 3 value proposition that I told you about, but there's an additional one that you see here, which is connecting to a GPU, because you need a GPU for large language models when you need that hardware acceleration from a GPU. But how do you do it in a way that data that is moving from the CPU to the GPU is protected and it's not getting tampered with by somebody else? So before hardware level protection shows up, there is a software solution that Intel and NVIDIA in partnership with Google brought to market called the encrypted bounce buffer solution. So it allows you to transfer data from the CPU to the GPU in an encrypted fashion. Surprisingly, even in software, it's fairly performant and very well being deployed with customers today who want to use the combination of the CPU as the head node and the GPU as the accelerator node. This becomes even better when you have TDX Connect, which is built on a industry standard called the TDISP protocol, which is basically a hardware encrypted channel between the CPU and the GPU. And this is something that will come soon, and hopefully when Nelly invites me back next year, we'll talk about solutions that take advantage of TDX Connect on GCP with NVIDIA and other accelerators. Okay? So this is a range of solutions. The first 2 are available today, and the next one is going to be available soon. This is really around attestation. This is really showing you that there is the ability to provide attestation across all these options. Intel has its own attestation service at no cost to give Google customers the option to get an independent trust authority. Pardon the pun, Intel's attestation service is called Intel Trust Authority. To give you that independent attestation, it's multi-cloud, it is completely independent. For customers who want that extra level, that they don't want the infrastructure provider to be the attestation provider as well, you have a solution on Google Cloud today. So you have that capability as well. Now let me move to sovereignty. A lot of you probably think of sovereignty and you think of location-based sovereignty, which is where it has been, right? It started off in countries who are very protective about their data. Countries like Germany, where they want to protect, and they have these data centers in Germany because that's how they want to protect their denizens, PII information. But data is very fluid. One misconfiguration, one software error somebody can get access to data that they should not be getting access to outside the sovereign region or wherever you are. This is where Intel TDX helps you as well, because you now have the ability to control your data and give cryptographic proof without needing just a geolocation capability. So that's where I believe Intel TDX and its host of technologies provides you that data confidentiality, that data sovereignty, and supports you with all these upcoming AI usages that you're all probably thinking about right now, and making sure that your data is protected at every step of the way. Okay, with that, I'm going to hand this off to Amit, who's going to continue our conversation.
Thank you, Anand. So we saw a lot about how Intel TDX sets up the foundation to get confidentiality, integrity, and verifiability, right? All using the hardware root of trust. So, but in the world of accelerators and in the world of AI, your end-to-end system needs to be confidential. So this is where I'm going to walk you through how we do it with GPUs and what it really means, right? So this is your standard TDX machine. The ephemeral keys are generated. They're all in hardware. Nobody has access to it. Data is continuously encrypted. And you have the same three tenets: confidentiality, integrity, which really powers all the isolation between VMs, as well as verifiability, which ensures that nothing on the hypervisor, nothing at the host layer, none of the privileged administrators have access to anything. But what happens when you add GPUs to the mix, right? So with GPUs added to the mix, you now need end-to-end confidentiality. This is where the NVIDIA driver that is sitting inside the guest VM is working in tandem with the GPU on the other side to provide guaranteed encrypted data transfers between the CPU and the GPU. So what does this really mean in a simplified fashion? So if you look at the diagram on the left-hand side, when there is no confidential compute, the data transfers are all in the clear. You can see the host or the hypervisor layer has full access to the NVIDIA GPU, which is the high bandwidth memory, as well as any transfer that is happening between the CPU and GPU is all in the clear text, right? So this is exactly what confidential GPUs addresses. Now we have the NVIDIA driver sitting, works in tandem with the GPU on the other side, and ensures that these transfers are no longer in the clear. The data transfer is all encrypted end-to-end, as well as the hypervisor does not have any read or write access to the NVIDIA GPU. This is the simplistic version of what actually happens, right? And all of this guarantees you hardware-based isolation and security. Everything is protected. Anything on the PCIe bus, which actually enables the transfer, is protected end-to-end. Not only that, there is cryptographical guarantees on all of this, right? The GPU verifies that it is actually talking to a confidential CPU on the other side, and only then the entire system comes up. So you're assured that everything is confidential end-to-end, and this is guaranteed by hardware-backed root of trust. Not only that, all of this happens at line rate. Because there is hardware-accelerated encryption, there is a minimal performance overhead, because this is one of the top of mind for every customer. What is the performance impact? You are encrypting data, right? And we have actually benchmarked this against the Llama 13 billion model. And as you can see, the performance impact is in low single digits. All of this happens at line rate, and there is nothing that you need to do separately within your application. Everything gets enabled by default if you simply turn on a checkbox inside of GCP. Of course, these numbers are benchmarked for a particular model. I think based on your application and the model that you're using, you could see a variation, but we still expect the overhead to be very minimal. Now, this is everything that we have talked so far is all about data in use. But security is really defense in depth, right? So there's data in transit, there is data in use, and there is data in rest. We talked a lot about data in use, data in transit. We have TLS, so that addresses most of your issues. If you have not already attended, yesterday we announced a prompt encryption SDK, which is an open source SDK, which you can actually use in addition to the infrastructure layer guarantees that we provide to encrypt your data in use. But data at rest is also super critical. And this is where we have different flavors of KMS solutions that exist. starting with Cloud KMS that provides you software keys that are controlled by the customer. We make it very easy using our auto key feature where keys get created on the fly as you want. And you can use these keys not only to protect data at rest, but also to protect your prompts and responses as they get generated. You can turn up the dial further and start using Cloud HSM, and you get FIPS 140 level 3 protection with hardware-backed keys, and all with the same assurances and scalability that cloud provides, no operational overhead that the customer has. You can simply choose the keys of your choice, and everything works out of the box. This year, we've gone one step further and provided what we call as a single-tenant HSM. What single-tenant HSM does, it takes the same Cloud HSM and gives you complete administrative control over a single partition. This guarantees that your keys remain only in your partition. Your partition is not shared across customers, and again, with the same benefits of cloud. You don't have to worry about the supply chain. You don't have to worry about provisioning. You just ask for a single-tenant HSM. You get a dedicated partition that scales with cloud as you need. Again, if you want to dial down your security needs even further, this is where we have the confidential external key manager. We always had an EKM, an external key manager, that needed a partner. Now we provide you the same capabilities where you can have a root key that sits outside of GCP, which you control, and with minimal latency, the same SLOs, and at a fraction of the cost. The confidential EKM is also available in preview. You can try all of this. So this provides you the same guarantees on data confidentiality and security for data at rest. Now, how does all of this come together? So we have put together a small demo as to how this all works in tandem and how you could leverage this to protect all your data. No demo in this next will work without agents. So it's all, we are in the agentic era. So we have a small agent that we have put together, which is a clinical health agent. And this works with a fine-tuned Gemma model. And users can send their health queries to this particular agent. It talks to an MCP server, and it has access to all the user's health record. Now, if you look in this scheme of things, we have highlighted in yellow all your sensitive information, all the data that you would really want to protect end-to-end. Right? So you have prompts and responses that the user sends, which is sensitive information. Your agent's memory and the context window is, again, super critical. You want to make sure that nothing gets tampered with, nobody is able to modify it, and it has the integrity guarantees that we talked about. You have your models and weights, which are fine-tuned and which are important. This agent and the model, when it is making calls outside, it has credentials to make the tools call. You want to make sure that those credentials don't get compromised. And last but not the least, the user's health records that are residing on disk are also critical. All of this needs to be encrypted. We are going to walk through a small demo, which is pre-recorded, which will talk about how we protect this end-to-end.
Hello, everyone. Today, I want to show you the future of secure clinical AI, an AI medical agent built entirely on Google Cloud. In healthcare, data privacy is the absolute highest priority. We can't rely on standard web apps. We need hardware-level protection. That's why we've built this agent using Google's Agent Development Kit and deployed it on Google Kubernetes Engine nodes enabled with confidential computing. By using these specialized nodes, we create a trusted execution environment. This means the memory processing patient data is encrypted at the hardware level. Even the hypervisor, host OS, or cloud administrators cannot see the data while it's in use. Our agent uses the Gemma model for reasoning and communicates via the Model Context Protocol, MCP server. For the communication with MCP server, API key is fetched from Google's Secret Manager. Because the entire workload stays within this encrypted enclave, the link between the AI and the medical records is shielded from external inspection. We are ensuring that clinical intelligence and sensitive records never exist in plain text, providing a cryptographic guarantee of privacy for every patient.
Let's look at what happens when we try to interact with an ADK agent running on standard, non-confidential GKE nodes. Notice that the system immediately flags the session as unsecured due to failed attestation. Attestation acts as a digital verification mechanism, ensuring that confidential data is only processed within hardware-based trusted execution environments. Now we will see the agent deployed on confidential compute-enabled cluster. If we scroll down to Node Pool section, we can confirm that our agent's strictly scheduled on confidential node. Additionally, we can check the node where our agent is running. We can see the label confirming that it is confidential node. As we have deployed the agent in a confidential cluster, the attestation checks are successful, and the clinical health assistant is now enabled. Watch as the agent securely requests access to private health data to provide personalized medication recommendations and practical travel precautions. Sensitive user information is now being processed and is encrypted end-to-end. All the prompts and responses are encrypted. Let's revisit the end-to-end secure flow. When a user submits a request through the web portal, the Google ADK agent intercepts the query. To ensure the data is protected in use, the agent and the fine-tuned Gemma model run exclusively on GKE confidential computing nodes, authenticating securely via workload identity. Recognizing the need for specific patient data, the model prompts the ADK agent to execute a tool call to the MCP server over an isolated, secure internal network. The MCP server then retrieves the requested medical records from a cloud storage bucket, where the data is strictly encrypted at rest, and securely decrypts it using Cloud KMS. Finally, the raw metrics are passed back into the confidential computing environment for the Gemma model to format a clinical summary. This summary is streamed directly back to the user's browser over a secure connection, guaranteeing that sensitive patient data remains completely protected, encrypted at rest, in transit, and in use throughout the entire lifecycle.
So we have all these building blocks that you can use. If there are more questions, we are happy to address that. But let me call Nelly to describe what we have coming up ahead, as well as how some of our other customers are using this.
Thank you so much, Amit and Anand. Wonderful conversation so far. So I'm coming on the stage to announce a new addition to our family. We will be able to, again, provide to you, our customers, a new type of GPU. This GPU is called RTX Pro 6000. Please don't, again, confuse this one with workstation version ADA. This one is cloud enterprise version, specifically built for cloud. This is very powerful RTX machine, and it's connected in our vault with AMD head node, also supporting confidential compute natively from start. This GPU, compared to the ones that we have even higher HBM memory, 96 versus Hopper 80. It has really strong performance characteristics. And what we've seen that our customers that bring in what we call domain-specific models specifically would like to use this kind of capability. One additional thing that we want to highlight about RTX Pro 6000, that it will have global availability on every region that you would run your AI-specific or agentic AI workloads. It will be ready for you, end-to-end confidential. So stepping back, let me again discuss our confidential AI family. We have GPUs for any size of the workload. So last year at Next, we introduced H100, and it's the first ever GPUs that support confidential compute natively end-to-end. And it's connected in our configurations as part of A3 machine family with Intel TDX systems. We also, as you see, introduced mid-size RTX Pro systems that connected to AMD head node, and we have and continue working on Blackwell GPUs that will come later, and we will announce that, and those are specifically targeted to significantly bigger, large foundational models that our customers bring in to GCP. So we will have GPUs for every single type of model and every single type of your use case. So why confidential compute becoming more important? As Anand mentioned, and very properly so, sovereignty requirements are becoming more and more prevalent. And even in data residency use cases, there is very much demand of protecting IP. One interesting use case that we have, maybe you're familiar with Google Distributed Cloud product. And this product, when we enable customers to take the racks right into their on-prem stores or on-prem data centers. No surprise, our customers demanded Gemini, and Gemini is Google's highest IP. So we are exactly in the same position as any customers bringing their models to us. We bring in our models to the systems and their locations where physical access to those machines available to operators and any other insiders of these companies. So what we do, we use confidential compute to protect our own models on GDC. And if you will be, again, seeing those presentations, you probably will recognize the same capability. So we have another sovereign product that also probably you're familiar. It's what we call Google Cloud Dedicated. And sorry for our naming. I know it's complicated. Between GDC and GCD, even us sometimes we get mixed up. So GCD, or Google Cloud Dedicated, is specific GCP deployments that are operated by third-party trusted vendors, in particular SANs, and we have that in France and Germany, and looking forward to expand it other places. And when customers coming to those specific deployments, they also very worry about operators being in the trust boundary. So confidential compute here to help to, again, address their concerns and fears for sovereign story. And what Amit mentioned, confidential external key manager, also very important piece of technologies that we provide for our sovereign customers. Why? Because our customers looking for ability to control, have possession and custody of the most important assets, their keys. And the ability for them to control it and pull the plug whenever they need is super critical for sovereign use cases as well. So confidential compute and external key manager together with our key access justification property gives them this ability, and it's very highly demanded sovereign product as well. So let me talk about a few customer use cases. So we talked about technology, we talked about what, but let's talk what our customers doing. Probably some of you know what Swift is doing. How many of you never heard about Swift? Raise your hands. Okay, let me explain you. This is probably the biggest financial, again, backbone system that we have in the world. Swift has millions and millions daily messages they process. One stat that they shared with us publicly is incredibly interesting. The whole entire world's GDP is going through their systems in 3 days. It's a very important company, to say the least. And one of the things that they very, very much focusing is fighting financial crime. And financial crime is coming to fraud. They, again, quoted us at almost $500 billion they spend yearly on the fraudulent transactions. So imagine that you need to fight those fraudulent transactions. And to be able to detect that, you need data coming from different banks. Having data from single bank would not help you at all, because you can only see whatever happening here. But you need to collect this data and combine and ingest it from multiple sources, multiple banks. So now ask yourself, how many banks happily will share the data with Swift or anybody else? Nobody. So, but again, what Swift did, they created this very interesting, next slide, very interesting model that they run in confidential environment. And this confidential environment can guarantee that not Swift would see or get access to any data, and not any of those banks that contributed their data sets would be able to get access to each other's data. So it's incredibly important properties that allow what we call federated intelligence or collaboration. Next, completely different use case. This one is very interesting to me because we're always talking about training and fine-tuning and inference. But by the end of the day, one of the most important things, when you build your domain-specific model, you need to ensure that it does what you expect. You need to benchmark it. You need to figure out efficacy of these models. Now, the use case that MedPerf is trying to solve is very interesting. So there are models that build by hospitals to figure out how to fight glioblastoma. I can't even pronounce it, but it's incredibly serious cancer that actually most likely terminal. Detection of this brain cancer and, again, treatment is paramount. So now, to be able to test efficacy of those models, you need to be able to share this MRI, brain MRI, with this model. And again, ask yourself how many hospitals would be able to share patients' information, so sensitive information to be able to do it. Again, the solution, confidential compute. They running their benchmarking in confidential compute in GCP to be able to provide those boundaries, this cryptographic isolation and verification, that giving all of those hospitals proof that their data and data of the patients continue to be private. We have incredibly interesting demo, by the way, it's very long, so it's in our booth, but if you're interested on MedPerf effort, please stop by our security booth. So now I'm switching a little bit to another topic, but very important, and the topic that I'm incredibly passionate about. Not talking about confidential compute. And it's post-quantum cryptography. So all of the privacy guarantee and all of the things that we discussed today, it's all built on cryptography. It's built on encryption. It's built on signing, digital signing. It's how we will ensure integrity and tamper evidence. And let me introduce to this character. And this character is very, very interesting personality. So again, we're talking about Willow. Willow was introduced by Quantum Labs in Google by end of 2024. So I would say it's probably 18 months old. And it's demonstrating very effective and very interesting behaviors. So again, it can perform incredibly fast operation, sometimes so fast that, again, you don't have enough zeros to describe it. So they have 10 and 25, power 25, you probably read the article, ability to do some sensing. Absolutely useless operation between us, but it's, again, the normal computer will take enormous amount of time. This, 5 minutes. The error correction is keeping stable as we increasing qubits. And again, this year, another milestone was reached for the same research is ability to create reproducible results. It means multiple chips can come to the same results without any problem. And it means that quantum is coming, and it means that our cryptography will be broken. And the problem that we have, we as all of us, changing cryptography with all agility is paramount and very complicated. Let me again remind you, ECC, the things that we are so used to, took 2 decades to get along. AS, 1 decade. And now we have probably 2, 3, 4 years until quantum is becoming reality, and we need to do something about that. So the problem also with post-quantum algorithms that become standard, despite of the fact that cryptoanalysis is still going, with all of those algorithms, it's not drop and replace. In previous world, we had this luxury that we can replace those algos very easily and everything continue, no problem. With post-quantum lattice-based modules, it's much more complicated. Or signatures are too big, or keys too big, and it's a problem. So in our world, what we're trying to say, there is not all cryptography is susceptible. So one thing that you need to watch for very carefully, and please, please, it's not a problem for 3 years from now. This problem is today. You need to watch for asymmetric cryptography, where it's used in your, again, workloads, in your applications. And asymmetric cryptography is the most susceptible to quantum threats. So we're talking about RSA, ECC, etc. And asymmetric cryptography used in 2 different scenarios. When we're creating the MTLS or TLS connection between endpoints and we negotiate the keys for this session to encrypt this session, it's where we'll use ECDH or ECC-based asymmetric cryptography or RSA, depending on the case. And in Diffie-Hellman exchange, we do need to move to already standard key encapsulation, again, mechanism, CAM protocol for these particular things. And the reason why, because the thread that we all worry about, and you heard about that probably million, trillion, zillions time, it's stored now, decrypt later. And it means every sensitive bit and byte that you're sending over the wire that's not protected and not quantum resistant can be stored now and decrypt when those computers will become available. And it's definitely something to think about. Symmetric cryptography, don't worry about that too much. And the reason why, because symmetric cryptography mostly used for bulk encryption. And for IS-256, it's already proven that it can sustain quantum attacks. So it's quantum resistant, and it means if you're using AS-256 bits, you should be okay. Don't panic yet. If you're not, again, my cryptographers told me, Nelly, even 128 will do just fine, but it's again NIST and everybody suggested to go to 256 bits, so please do that. All cloud providers, us included, support all of that, so we're ready for you whenever you're ready. And fancy cryptography, again, because it's not used very often, we are not worried about this too much. So what Google does about that? So we scared you a lot. As usually, security people love to do that. But what do we do to help you in this journey? We do a lot, honestly. From 2016, we absolutely involved with NIST and doing a lot of experiments on different crypto algorithms. But most importantly, we have made significant progress, and all your Chrome is quantum safe. If you will go, and you can test it whenever you're ready, go to your Chrome, come to our google.com, push F12, and see what you will see as our, again, connection to TLS. If you will see MLCAM, you know you're in good hands. So now, our, again, public sites, including front and cloud sites, is all also MLCAM capable. And that means we negotiate the session, and this session is fully protected. Your collaboration apps, our workspace, it means your Gmail, calendar, everything is also, again, MLCAM capable. And it means from the proper client, proper site, it will create the quantum resistant session. So you will be in good shape as well. What we worry about and where we need your help, if you're using some homegrown crypto, highly discourage you to do, but if you're using that, or using any library, please identify in your applications, and we have absolutely a lot of tools for you, what you're using and how you're using, because you need to validate your performance, your latency, and compatibility with FIPS supported and approved algorithms. We have open source libraries for you. Please use or boring SSL or OpenSSL 3.7. So everything is ready. Please do that. In Cloud KMS, we have all of those algorithms implemented in software. Hardware is still a little bit behind, but you can use Cloud KMS software keys with MLCAM, for signatures, MLDSA as we called, or SLHDSA for your, again, signing firmware or signing root of trust. All of that ready for you to use. And finally, as I said, it's fully integrated from your client to our applications to cloud. Everything is MLCAM capable, and we're happy for you to use that and ensure that your communication is safe. And now, let me introduce to you again Anand and what Intel is doing in post-quantum vault.
I'm going to make this very quick. Intel has a two-pronged strategy for PQC. The first one is to protect our own platform. So starting with Xeon 6 that launched last year, we are starting to provide PQC-capable support in our hardware, and that will continue till 2029. We started that conversion, as I said, with Xeon 6. We're increasing our coverage generation over generation, and by 2029, we'll be ready. Now, we're also providing hardware-based acceleration. As Nelly mentioned, AES 256 is accelerated. It's available today. So please use it, because you don't want to be stuck in the harvest now, decrypt later kind of attacks, because the time is not 3 years out. The time is now. And we'll continue providing acceleration for asymmetric encryption and expanding for PQC algorithm acceleration in future generations of our platform. Okay? Nelly, back to you.
Yep. And it's again, to finish our presentation, sorry, we kind of get a little longer than we expected. So again, the future is today. And we're talking about collaborating with our partners, NVIDIA, Intel, AMD, ARM, to bring confidential compute as a reality to you. Confidential AI, you remember models, data, agents need to be protected. Sovereignty is important to have absolute, again, guarantees that nobody would be able to see your model, your data, your agents, and post-quantum is coming, and we need your readiness, we need your help to get ready, and by 2029, Google will be completely going to post-quantum safe vault. We hope that you will join us in this journey. Thank you so much. If you have any questions, we will be, again, available for you as well in our discussion group. But thank you so much for staying a little bit longer. Appreciate your attention.